My name is Stan Wojcicki, and I have distinct pleasure and honor to introduce today's panelists, and first to say a few introductory remarks about the topic of forthcoming discussion, namely the neutrino physics. As I introduce the panelists, I would ask you to stand up and take a seat over here so you're very much visible and prominent. So I want to start by introducing the panel's moderator, Yuri Milner, someone who really needs no introduction. Yuri is the founder of the Breakthrough Prizes, viewed today as the most prestigious recognition of accomplishments in science, a truly Nobel Prize of the 21st century. So why don't we give him a hand for his... Please sit down, Yuri. Okay, I will turn now to neutrinos. Since their postulation by Pauli 85 years ago and their first observation by Cowan and Rines 25 years later, they probably posed more questions than provided answers. They were known to have very tiny mass or no mass at all. But if massless, what symmetry principle dictated that? Did they have any new interactions with matter besides the known extremely weak interaction? Were they their own antiparticle? What role do they play in cosmology or composition of our universe? Are they responsible for matter-antimatter asymmetry and hence for our existence? The list goes on. In 1960s, it was already known that there were two species or flavors of neutrinos, muon and electron. Subsequently, a third lepton flavor was discovered, the tau. Bruno Pontecorvo pointed out already in 1967 that if neutrinos do have small but non-zero mass, then they can mix and oscillate, i.e. neutrinos of one flavor can change into another one as they propagate through space or matter, and then they can change back again. Whether they have mass was unknown, but it was known that it is at most 1,000,000 times smaller than that of the lightest known particle, the electron. Thus, if neutrinos mix, the description of a general neutrino state could be expressed either as a linear superposition of the three flavor states, electron, muon, or tau, or of their three mass states. These two descriptions would be related by a unitary 3x3 matrix. The overarching questions in the 1980s, when the story we shall hear today begins, were, do neutrinos have mass? And if so, what are these masses? Neutrino masses imply a mixing matrix with four independent parameters. What are these parameters, and how can they be measured? What dictates the values of these masses, of these neutrino masses, and of these matrix elements? What causes these masses to be so incredibly small? Several anomalies in neutrino experiments were observed already in the 1980s, which could potentially suggest oscillations, but there appeared to be contradictions, and the idea of oscillations was viewed by many as unlikely and outlandish. A new generation of experiments was needed to address these questions. As you will hear, a tremendous progress has been made since that time, and our panelists were the key players in this evolution. But some important issues remain unresolved, as undoubtedly you shall also hear today. Let me now introduce the panelists and try to connect their work to the issues I just mentioned. First, Takaaki Kajita and Yoichiro Suzuki, leaders of the Super Kamiokande experiment. Please come and sit down. Taka is currently director of Institute for Cosmic Ray Research, ICRR, in Tokyo. Yoichi is the director of the Kamioka Observatory at that institute, and also deputy director of the Kavli Institute for Physics and Mathematics of the Universe. They addressed, respectively, the apparent disappearance of muon neutrinos in cosmic rays and of electron neutrinos from the sun, using a very impressive 50-kiloton water Cherenkov detector deep underground. I might just say that it could be that this detector will prove itself to be the most efficient and productive detector ever in high-energy physics. Art McDonald is Professor Emeritus of the Queen's University in Kingston, Canada. Art? He was the leader of SNOW, the Sudbury Neutrino Observatory collaboration, that addressed the so-called solar neutrino puzzle problem, an apparent deficit of solar neutrinos reaching the Earth. To accomplish that, he and his collaborators spent well over a decade designing and building a 1,000-ton heavy water detector deep underground in Sudbury, Canada. That commitment took a lot of courage and conviction, since initially there was some skepticism whether there really is a solar anomaly. To give you a flavor of that, let me quote one Nobel Prize-winning theorist. Most likely, the solar neutrino problem has nothing whatsoever to do with particle physics. It is a great triumph that astrophysicists are able to predict the number of boron-8 neutrinos coming from the sun, as well as they do, within a factor of 2 or 3. Okay. Atsuto Suzuki is the director of Japan's High Energy Research Organization, or KEK, in Tsukuba, Japan. He was the founder and leader of the COMLAND collaboration, looking at antineutrino interactions coming from all Japanese reactors with a detector of 1,000 tons filled with liquid scintillator and located deep underground in the Kamioka mine in Japan. COMLAND complemented SNOW detector and SNOW experiment in determining with high precision the parameters relevant to electron-neutrino oscillations. Next, let me introduce Yifeng Wang and Cambio Luk, leaders of the Daya Bay experiment located in China. Yifeng is the director of the Institute of High Energy Physics in Beijing, China. Cambio, a professor at University of California, Berkeley, and a senior faculty member at the Lawrence National Berkeley Laboratory. They conceived, designed, and built, and subsequently led the analysis effort for an experiment at Daya Bay in China that consisted of 80 detectors in 3 locations containing 160 tons of liquid scintillator and looking at antineutrinos from 6 nearby reactors. The goal was to measure precisely one of the mixing parameters that was relevant for the electron-neutrino oscillations, and at that time was not measured and was thought that maybe it's even 0. Let me just. Okay, sorry. Oh. I thought for a moment that I lost one page. That would be terrible. Okay, finally, Koichiro Nishikawa. He would never forgive me if I had done that, because he's an old friend of mine. He's the director of the Institute for Particle and Nuclear Studies at KEK, and KEK deputy director. He was the founder and leader of the 2 neutrino accelerator experiments in Japan, K2K and T2K. The second one still in progress. The experiments looked for oscillations of neutrinos, and the results cemented our knowledge of neutrino oscillations. Might add that these experiments were the only ones discussed today that had to generate the neutrinos for the studies. In all the others, the neutrinos came for free, courtesy of cosmic rays, the sun, or power companies. Finally, few concluding remarks before I hand the mic over to Yuri. As you can see, the prizes of this year recognize contributions of large experimental teams. As an experimentalist, I am delighted to see that. Invariably, the success of these experiments is due not only to the creativity, originality, and leadership of the people at the top, but also to frequently insufficiently recognized efforts of countless students, postdocs, engineers, and junior faculty members. They should feel proud of these accomplishments and this recognition, and we should also give them a hand. Okay, Yuri, your game.
Thank you, Stanley Wojcicki, for introduction. I want to add one more thing to this introduction, which is to say that when the selection committee of Breakthrough Prize made a decision to award Breakthrough Prize to the 5 experiments this year, we did not know that the similar thought process was taking place in Sweden. So we have two panelists today, which is Takaaki Kajita and Art McDonald, who were also awarded Nobel Prize. So let's. So obviously they have a much easier logistical problem than we do, because we have to track 1,377 people and send them the checks. So I think it will take about 6 months to do that. So the first question I want to open the panel with is to ask everyone. What are the big open topics in neutrino physics and maybe even in the particle physics in general? So maybe we'll start from that side.
Okay, well, in my opinion, maybe I cannot say particle physics in general. I want to say about the neutrino physics only. Well, in my opinion, I think there are 2 big questions to be solved or understood. That is, one is the CP violation in the neutrino sector, and also we'd like to know if neutrinos are Majorana particle or Dirac particle. These 2 are, I think, the most important questions to be understood in neutrino physics.
I say slightly different things. Because then that, everybody here is physicists, right? So I say rather in the different view. So the particle physics, and of course including neutrinos, is a kind of the aim, goal from our curiosity. That is a beginning. So general public forget about these things. What is a basic science, physics science is really starting from curiosity. We should come back to that point and again.
Arthur?
Well, I certainly agree with Professor Kajita about the 2 topics that are mentioned. And I think one of the nice things about the developments that these experiments have made so far is that they've created low radioactivity underground environments where you can do a number of things. certainly neutrinoless double beta decay in terms of both the Majorana nature of the neutrino and also the perhaps absolute mass of the neutrino is a very important topic to be pursuing. But we also have a very big puzzle in terms of dark matter, which is both a particle physics and a cosmology and astrophysics question as well. And these underground environments give us great opportunities to do direct detection of such particles. So I would add those. I would add that.
Yes.
Okay, I have similar opinions. One is we still don't know the absolute scale of masses, neutrino masses. Neutrino oscillation produces the mass difference, not absolute masses. So our next step is to determine the absolute scale of the neutrino mass. This is one future target. The other one is, Kajita-san said, Majorana or Dirac particle. This is also open question. Another one, we don't know why the neutrinos, neutron masses are so small, very small, comparing the other particles. Then we need to understand such mechanism. In order for us to do, we need to produce the direct production of heavy neutrinos. So in future colliders, electron-positron collider, future colliders have a chance to produce that heavy neutrinos. This is our very key subject for future neutrino experiments.
I take the question to be a long-term physics goal. And in general, for the long-term question, the basic question is simple, I think. What is the flavor and those three generations? Is it closed by the three generations or not? I think it's a basic question we have to address in a long-term program. And I think the high energy physics should question our basic stance, basic scheme, like a three generation 3x3 matrix. Is that closed or not? That eventually it must be checked with experimental observation.
Well, in the neutrino sector, I do agree that knowing the nature of neutrino, that is, okay, whether it's a Dirac type or Majorana type is a burning question. Because, okay, if we know that would help, say, the theorists, to build model. And if we now believe neutrino, points to, okay, say, some crack in the standard model, then that means, okay, there will be physics, okay, that we haven't learned before. So one experiment that would be important will be, the proton decay, because, okay, certainly there are, the new models, that predict, that should happen. So doing that kind of experiment will guide us, okay, in the right direction. And also, I agree, the dark matter certainly is really, critical. However, personally, I have no idea what dark matter is. So at this moment, I don't have a clear picture, how to tackle this problem. And then at an even higher scale, we know, certainly that we cannot continue to build an accelerator, bigger and bigger. Like Fermi said, okay, well, build one around the equator, and I don't think we can afford that. So, one way, we may be able to get some idea about, say, the very high energy scale is, okay, look at the cosmos in particular, okay, whether the inflation theory is correct or not. So I would, okay, certainly invest, okay, in that area along with, okay, other experiments.
In addition to all the neutrino problems, people have mentioned before. I think we have other issues like neutronics problem, the hierarchy problem, and so on. So with the discovery of Higgs particle, it seems the standard model is complete, but we believe it is still an effective theory. There should be physics beyond that. So we need newer colliders, higher energy machines to look for physics beyond the standard model.
Yes, thank you. Thank you for addressing this question. I've been looking at the list of winners, and I've noticed one interesting formula that 3 out of 5 experiments are located in Japan. So, what is so special about Japan in terms of neutrino physics? Takaki, you wanna?
Okay. Oh, difficult question. Well, I don't find any special reason for this fact, but, well, at least I can say that we are fortunate that we had Super Kamiokande operated already in '96. That is about 20 years ago. And, well, this had a real boost in the neutrino studies. Well, first of all, we were able to do atmospheric and solar neutrino studies. And, well, because the Super Kamiokande was built, then the cavity for the Kamiokande was empty, essentially. Therefore, another experiment, Kamran, was able to run. And in addition, Super Kamiokande is a big detector. And there was an idea to use Super Kamiokande as the far detector. So, in my opinion, I think the key was the early construction of the Super Kamiokande detector. And I'd like to mention for this early realization, we would like to thank late Professor Totsuka for his great effort for this.
But experimental physics in Japan, it seems like there is a lot of investment going on in Japan in that area. Can you comment on this?
Yeah, but well, I think we have the environment to really invest money for this area.
Well, another observation I made was that 4 out of 5 experiments were made in Asia. So Yifang, can you tell us why why China decided to focus in this area?
China is a latecomer particle physics. We only started the experimental effort in 80s, I think. With this E+ and minus collider in Beijing, we managed to build up team, the community, and then fortunately in the beginning of this century, we have this opportunity to build up a neutrino experiment in China, thanks to the power plant nearby, and there is also a mountain, so you are able to build up this experiment. And relatively speaking, this is a small-scale experiment compared to all the other particle physics experiments. So I have to say we are very lucky, and also with this small investment, we got some results.
Yes, please.
One thing?
Yes, please.
Okay. In Japan, we think that continuation is essential. Don't stop the research activities by budget cuts. For instance, in Kamioka, we started, I joined Kamiokande experiment for Kamiokande experiment 30 years ago. Kamiokande, after the Super Kamiokande, then Kamran. Now Kamran is now going to the next second generation experiment. And also in particle physics, Japan also started the electron-positron collider, Tristan, then KKB factory. Now we start the Super KKB factory soon, next January. Also, we are so much eager to host linear collider for next generation. Therefore, continuation. This is essential for keeping the activities.
Yes, please.
When we started the K2K, we had a good, excellent competitor in US also planned to do the experiment from Fermilab to the new detector. And I think of course, in addition to those Kamiokande site already exist, US had an excellent accelerator, and we had a relatively inferior accelerator in Japan. So we had a good competition in starting up the long baseline experiment. And looks to me, I'm already retired, so I can't say anything, but looks to me the big difference was the decision-making process of a future plan. We had the right person at the Director General at KEK to decide, go ahead with the K2K. And that had a big effect. And I don't know the system, what's going on in US, or I only know from outside. So I can't compare directly, but it was a big effect. Right decision-making person at the right place.
I'd like to add one thing. I'd like to add what Kajita says. And there was 2 water Cherenkov detectors before Super Kamiokande. One in Japan, Kamiokande. The other one is the IMB in the United States. Size is much, much bigger in the IMB. IMB is 8,000 tons. Kamiokande is 1,000 tons. But the difference is the size of the light sensor. And the Kamiokande uses 50 centimeter diameter, and the IMB is 8 inches. So that makes the energy resolution and the energy threshold different. So Kamiokande are able to detect solar neutrinos, but the IMB didn't. Then the Super K and most of the IMB people and Kamiokande people come together and build Super Kamiokande. That is a joint effort in Japan and the US.
May I add a few words? Well, since I am the only U.S. researcher in this panel, maybe I can add a few words. When I came to the U.S. for graduate study, at that time, the U.S. mentality was okay, can do. So every time when we came up with new ideas, essentially we could mount the experiment in a very short time. For instance, when I was a graduate student, basically I could do 2 experiments in 1 year. So people was very supportive, and people were willing to go out their way to help. And there were very little bureaucratic interference. However, nowadays I feel that the U.S. system has changed quite a bit. It's becoming very, very conservative. And a lot of time, even though we have ideas, however, before we can mount the experiment, we have to go through a lot of hoops. And I think this is slowing down progress and also costing the project a lot more than it should be. And I think this is hurting the U.S. scientific community. This is my personal opinion.
One country that violates my Asian theory is Canada. So why Canada, a relatively small country, was involved in this, and what is the status of experimental physics in Canada? Art, can you?
My kids have a term for that. It's pew. Not quite so small, about 1/10 the size of the United States. So, but before I comment on a couple of natural advantages we had in Canada in pursuing this project, let me point out this was an international project from the very beginning. Our 2 co-spokesmen of the group of 16 that came together in 1984 were Herb Chen from University of California at Irvine and George Ewan from Queen's University, and I'm actually very pleased that Herb's daughter, Christine, is here with us today, and she's an accomplished astronomer in her own right, so that's very nice. And so this really was an international project from the beginning, but the two natural advantages that we had in doing it in Canada were the availability of a very deep site, 2 kilometers underground, which we were fortunate to have the company Inco allow us to use, even though it's a very active nickel mine still. And the availability of heavy water in Canada, which we were able to borrow from a Canadian government agency, $300 million for 10 years for $1. That's pretty good leverage in any market. So we're very fortunate with that. In the 1980s, when this project was starting, it was difficult in Canada. It was large for Canada, and the funding agencies that had to come together to make it happen were a combination of agencies to deal with a project that was larger than what is normally funded. And we had good support from the US and the UK in the process of bringing it together. And so it was funded in 1990, and eventually the results that the prize is being given for were obtained in 2001 and 2002. But in 2003, Canada had actually changed substantially in its support for science. There has been very good support over the last, starting roughly 1997 or so. There's a program called the Canada Foundation for Innovation, in which $10 billion has been put on the table, essentially with a combination of federal and provincial support for equipment, predominantly, for basic research or applied research. And you have to multiply that then by that factor of 10 in order to get the equivalent in the United States. And in addition to that, Canada put forward a program in which 2,000 chairs in various sciences were put into universities across the country, 1,000 of them permanent support from the federal government, and 1,000 of them junior positions with 7-year terms renewable. So Canada actually put a lot of money into research and development starting in about 1997 under the previous Liberal government, and it was continued by the Conservatives. That produced a substantial impact in terms of the ability to do research and development in Canada. So by the time it came to 2003 and the SNO results demonstrated that the particular location we were in was a valuable one in terms of the ability to go on and do further neutrino physics and now dark matter measurements as well, once we learned that in the interim that neutrinos were in fact too light to be the dark matter particles and wanted to continue. And so SNOLAB was created, and in this case we actually were able to apply to a program where the intention was to bring international scientists to Canada to participate with Canadians. 3 separate national laboratories were created at the same time by a program that was put in place at that time. So I would say that in fact in Canada things have changed substantially over the lifetime that I've been involved in this neutrino physics activity, and it's pretty good right now in terms of our ability to go and seek new opportunities to do science. So since you asked.
Absolutely. Well, the next question logically would be, what are the experiments you're working on right now? Let's start with Takaki.
What I'm working on now?
Yes.
Yeah. Okay, well, actually, I'm spending... well, director job, yes. Well, of course, I'm spending much time for the director job, but well, for the spare time, I'm I'm working in gravitational wave project in Japan, which is called Kagura. That is underground 3 kilometer by 3 kilometer interferometer located in Kamioka.
What is the difference with the U.S. experiment?
Well, okay, U.S. LIGO is slightly bigger. They have 4 kilometer by 4 kilometer length. However, well, we have some special technology to be used, that is the cryogenic mirrors. Well, these interferometers are so sensitive, therefore even the thermal noise of the mirror is a problem. So we are going to cool down the main mirrors to about 20 Kelvin so that we can reduce the effect of the thermal noise. That's the difference.
Yeah, I'm still working on the neutrino fraction time. Then I mostly concentrate on the dark matter experiment. And we built the dark matter detector 5 years ago and called XMass, and which is the single phase rigid xenon detector. Okay. Why single phase? It's different from the two phase. Two phase is practically much better at this moment, and they could identify the nuclear recoil very well with very low background. XMass is slightly higher background. However, XMass has a sensitivity to E gamma events. So now you know we don't know anything about dark matter. A few years ago, everybody talking about the supersymmetry and the WIMPs. But these days, people start looking for other than WIMPs. So in that situation, the sensitivity to have E's and gammas is much, much desirable. So XMass is probably can work and do some kind of good contribution for the dark matter search. So I'm doing dark matter search now.
Art?
So I'm involved in two projects. I'm retired from teaching now, but still involved in SNOW Plus, which is a use of the SNOW detector for neutrino-less double beta decay predominantly. We replaced the heavy water with liquid scintillator. I'm actually very pleased to be here at Berkeley because Berkeley is a substantial participant in that experiment, and they were a very substantial participant in the SNOW experiment in the first place, and so it's a pleasure to be here with colleagues. That attempt is to load tellurium into the liquid scintillator in substantial amounts and to be able to address questions of neutrino-less double beta decay. There is also the potential to do solar neutrino physics, geophysics, geoneutrinos, I should say, and so it's a broad range experiment which we hope to have in operation later this year and progressing towards neutrino-less double beta decay in about 2 years. The other experiment I'm involved in is in dark matter. It's 4 tons of liquid argon, an experiment called DEAP, D-E-A-P, and we're actually hoping to turn that on within the next couple of months. And our hope over a 3-year counting period would be to have sensitivity about 10 times greater than the present level for heavier mass dark matter particles. WIMPs, essentially, is what we're looking for in this case. And so it's fun to still be actively involved in these experiments and not have to be the director anymore.
Let me ask you a hypothetical question. If you would pick one experiment that you would do without budgetary constraints, sort of in the next 25 years, what would that be?
Well, as you can hear, I'm interested in those two topics. I think...
How big can you go sort of in that time frame?
I was going to qualify that by saying that you say without budgetary constraints. I think there's a 100 million or maybe more, 150 million experiment that could be done that would push dark matter to the limits in which the background for atmospheric neutrinos in the heavy mass area would limit you. With respect to neutrino-less double beta decay, I think if I had all the money in the world, the limits are perhaps such that if you put $500 million into an experiment, which would have to be an international collaboration. And I'm actually pleased to see the way a number of the collaborations are recognizing that this is the case, and the present generation experiments are coming together to say, well, we have two different technologies, but we'll pick the best one and try to go for the largest one. I think the potential there of exploring all the way down to a region where you're fairly sure that you will have the opportunity to observe neutrinos double beta decay if neutrinos are Majorana particles is there. And so I would put my 500 million or so into that one if I had unlimited funding.
So 500 million is for you no budgetary constraints, right?
No.
Let's say you go. If you go 10 times more than 500, what would you do?
Well, for me, it's quite a price constraint.
First question was
Yes. So what is the experiment you're working on right now?
10 years ago, I had to give up my scientific activities because of moving from Tokyo University to KEK as a Director General. All jobs are administrative jobs, no science activities. Then since this April, I am now the president of local university, Iwate Prefectural University. So this has meaning. This means a serious point. So Iwate, the prefecture Iwate is the candidate site of linear collider for future linear collider. So all the time I am now working as administrative jobs.
I'm enjoying my retirement time, so let me mention since Yuri already talked about the T2K is still going on, so let me explain the main purpose of T2K. And T2K main objective is the studying immunity oscillation, and this is the unique advantage which the solar neutrino and atmospheric neutrino delta M square region contribute simultaneously. And that is a good best position at this moment to look for CP violation, obviously, in the neutrino oscillation. And people is, our colleague is doing the hard job to pursue that direction by both including power of JPAC proton accelerator and proposing a new detector in Kamioka site. And if I had 50 more years, the finding out the CP violation is one thing, but I want to point out that the real physics exists, not just finding out the difference of neutrino and anti-neutrino, but we have to look for what is the cause of CP violation if it were found in the neutrino sector. And just like quark sector was proved to be dominated by Kobayashi-Maskawa mechanism, but it's not necessarily true if the neutrino CP violation observed. And that may be a medium-term goal of the experiment.
Okay, right now, I am still working on Diabase because we still have, at least 2 more years of runtime. So the idea is, okay, after we proven that the last mixing angle is large, now we want to measure it as precise as we can because, okay, in the foreseeable future, probably the Diabase experiment is the only one that can really measure this, fundamental parameter, that well. And in addition, we are also working on a new experiment called DUNE, which is a U.S. European collaboration. So the idea is to use this experiment to study the ordering of the masses of the neutrinos. Because right now we know that the neutrinos have masses. However, we don't know how they are ordered. So this is something that this doing experiment can address very well. And in addition, we can also use the experiment to look at the so-called the CP violation. That is some kind of asymmetry between neutrino and antineutrino. So those are the two the remaining questions in neutrino oscillation.
So what would be your favorite one if you had unlimited budget?
Well, I am in favor of Art and the others' proposal. I think that certainly the understanding of the nature of the neutrino is very important. And since there are a lot of isotopes we can use for studying neutrino-less double-bit decay, so certainly there's a lot of room for new experiments. So if say we have the unlimited budget, I would just farm out maybe half a dozen to a dozen experiments so that they can look at different isotopes and see which one will give us the winning signal.
Yifan?
So with the success of the IAA, we managed to get Chinese government to support us to build the next generation react neutrino experiment. I totally agree with what has been said before. Continuation is very important. So this time we again we are going to build react-based neutrino experiment and also liquid scintillator technology. This detector will be a few orders of magnitude larger than diabase. So this is a 20 kiloton liquid scintillator detector with a size of diameters roughly 35 meters of acrylic detector. So this is what I'm trying to working on right now, and hopefully the experiment can be built by the year of 2020. And with this detector, we can measure the neutrino mass hierarchy, look at the supernova neutrinos if we are lucky, and also detect solar neutrinos and geoneutrinos and so on.
Now, I know that you're involved in big effort in China, potentially big effort in China to build a big accelerator. Is it the one that you would do if you had unlimited budget?
Yeah, of course. If we have unlimited budget, say billions of dollars or tens of billions of dollars, I hope that we can build a world's largest collider, starting from electron and positron phase to look for Higgs, to study in detail the Higgs properties, and also looking for signs of new physics beyond the standard model. And afterwards, in the same tunnel, we can convert this machine to a proton collider with roughly an energy of 100 TeV. And by doing this, you can really probe the physics beyond the standard model by, say, at the energy scale, is another factor of 10 higher than HC can probe.
How big is the projected size of this machine?
It is not, I think it's roughly 50 kilometers to 100 kilometers of circumference, based on the money, of course.
And with 100 kilometers, you would be able to reach those levels, energy.
Right, right.
And what is the realistic time frame for that project if there is some sort of a green light?
I would imagine something like for the electron phase 10 years from now to start with. And for the proton machine, probably you need to wait for 25, 30 years to get the data or to be probed to that phase. So it is a long journey.
And to what extent do you think it should be sort of an international effort?
Absolutely, it has to be international. I don't think any single country can do it by its alone, for many reasons. So we hope that this going to unite the world effort to build this large collider.
And how that relates to the CERN collider, which is currently in operation?
Certainly, we will benefit a lot from the experience and the technologies learned from CERN, and in the end, there should be only one accelerator. So we have to work with CERN together to see what is the best way to build this world-only collider and find the best place to do it.
And what kind of physics do you think this collider can study? You mentioned Higgs, but can you elaborate on this a little more?
Well, first of all, Higgs is the only particles with a spin 0, so we haven't seen any elementary particles like this. We need to study very much in detail its properties to understand whether Higgs is the composite or elementary, to understand whether there's any companion partners of this existing Higgs, and also all these couplings to the known fermions. And by doing this, we try to understand the property of Higgs itself, and also we like to know the self-couplings of Higgs. So this will tell you that the actual weak phase transition and types, what kind of this phase transition and the potential shape. With all these studies, we hope that we can find indications of new physics beyond the standard model, and then give us a way to, or at least tell us how we should build a proton collider.
So there is another incredible experimental physicist in the room, sitting there in the corner, Sol Perlmutter, who is also the Nobel Prize winner and Breakthrough Prize winner. I just use my power of a moderator to ask you a question. What experiment would you build if you did not have budgetary constraints?
I do think that right now there are some real opportunities in the astrophysics areas that we've been working in, where if we were able to build the full system we would like, we would be able to see space-based telescope missions, and there's also some ground-based missions that could be combined with it, where we think we would be able to get a much more detailed accounting of the history, the expansion of the universe, and the growth of structure in the universe. That would tell us a little about this part of the story that has to do with the dark energy, and perhaps even the bringing together of the questions of gravity and the other three forces.
So you're talking about the optical telescope?
Well, actually, it would probably be, at this point, you'd want to do a full range from, if you really had a budget for this, from the ultraviolet through the infrared. Because I think a lot of the story you can capture in these different parts of the wavelength bands that you otherwise can't reach. And this is one of the reasons why the space-based efforts are, I think, so important at this point. We actually think that it's a possibility that one of these desires may come about in the near future, but we're looking forward to seeing what happens.
And in terms of the main parameters, what would be the size of this, the scale?
Well, so far, the considerations that we've had have all been budget limited. So we've often held ourselves to something we thought was practical. But if you were really opening us up in this range, I mean, we should remember that we're now designing telescopes in optical and infrared on the ground that are in the 30-meter scale, and it would be a real challenge, and it'd be fun to see if we could try to do something like that in the space as well.
Okay, thank you. I'll probably at this point open the room for questions from the audience. Yes, Edward.
I guess I have a question for Art. So you're building the neutrino double beta decay detector now, but you said that for $500 million you could imagine one that would reach farther and go down to the lowest scale at which it's plausible, if nature doesn't conspire against us, that the Majorana mass ought to be. So I just wondered if it would simply be a bigger version based on the same idea, or what would you have to do to get down to that level?
Well, I think there's a question both of scale and also of technology, and there are a number of technologies that are being explored that are potentially capable of dealing with this, ranging from solid-state detectors, the Majorana and Gerda experiments, for example, where it would be a scale-up question in terms of the amount of material, as well as having to in all of these cases, deal with the low radioactivity requirements in order to get the background down in terms of trying to do this. Quarry experiment is also using bolometry to try to do this. There, I think you want to improve the technology for reducing the background. The question of scintillating material, cryogens that have the possibility of pushing down as well, such as the EXO experiment. And all of these technologies have different pluses and minuses, but all of them would need an amount of material which is at least 10 times, maybe 50 times greater than what we're dealing with today in order to get the type of sensitivity in a finite period of time, because you're looking for enormous, greater than 10 to the 25th year half-lives in this case, which means you have to have a heck of a lot more than 10 to the 25th atoms in order to get your measurements made if you really want to get there. So I think it's a combination of technology and scale that needs to occur, and I think all of these experiments can collaborate on the basis of how do we reduce the radioactivity. I think the question of choice among the technology, including liquid scintillator-based experiments like SNO+, is something that really needs to be an open and fair comparison between them, and then an international participation to try to do this, as you get in the accelerator field. I think these are important questions and things that the type of philosophy that has gone forward in terms of building international facilities like CERN is important to bring into this sort of area as well.
Question perhaps for laypersons. Can you give us an understanding of how we would measure dark matter on Earth? I mean, the interaction between dark matter and conventional matter is somewhat uncertain, and therefore, can you give us a appreciation as to would we be able to directly measure it, or would it be by inference? Dark matter experiments.
Why don't you? Go ahead. No, you do. You're measuring dark matter too.
Well, I don't know if I get your question correctly, but I would say that, and that it is necessary to make and observe the interaction directly to find it out, what kind of, the particles and dark matter is. Otherwise, you are not able to identify those things. So direct measurement is very much essential and important.
Art, you want to add to that? Art? No, you don't want to?
Basically, what you end up doing is looking for processes that could only occur as a result of a dark matter particle striking your detector. You would agree. So you put your detector in a location that is as low in other radioactivity processes as you can possibly manage, one of them being deep underground, and therefore shielding out the cosmic rays that might cause interference, and then very careful choice of materials in creating your detector, very careful understanding of what other radioactivity looks like in terms of the typically bursts of light you're dealing with in this case, or electrical pulses that represent what a dark matter particle would do compared to what anything else could do. And that's the process. It's a process of elimination of everything else. But you put it in a location where only dark matter particles and local radioactivity can possibly make events in your detector. And then you eventually end up trying to convince people that what you've seen legitimately is dark matter. And then you have seasonal effects that can demonstrate that dark matter behaves in a certain way. That's not exclusive. You can get seasonal effects in radioactivity as well, but that's the process.
Okay. The question Yuri asked was if there is unlimited fund, what experiment you would pursue. But I want to ask if there is no budgetary constraint, what the world should pursue. Of course, with unlimited fund, they should do everything, okay? But colliders or cosmic measurements, a lot of things, right? What would be your priority if you are the director of the world scientific community? That's the question, not what you would do, yeah. Anybody, I don't know, yeah.
Okay, my first priority is to do the proton decay experiment on the moon. No atmospheric neutrino backgrounds.
Yes, please.
I have a small question, which perhaps is a kind of follow-up to that last answer, which is how much beyond the super K limit on the proton lifetime can we hope for in an ideal experiment or in some imaginable future? How much better can we hope to do with proton decay? Anyone who wants to answer that?
15 years ago. 15 years ago, I proposed that the one big detector and the total mass is 10 megaton under sea. Then that reaches to you, brings you to 10 to 36 years for E pi naught mode. So that is the place in the under sea, because in 10 megaton, you cannot, you are not able, not easy to make a big cavity underground. So you have to bring that detector under sea. So.
What's the role for experiments like IceCube going forward?
As far as I can see, and they have to fight with the resolution and the threshold to do the proton decay. Of course, and they are making effort to reduce those things, and I hope and they can get some measurement on proton decay. But they have to first demonstrate, and their detector can work for proton decay.
We heard earlier about looking for dark matter, but what about dark energy? How can that be found?
Saul should answer that.
So far, all the ways that we have to get at dark energy have been essentially looking at its effects on the expansion history of the universe and on the clumping of material in the universe. But there have been just a few thoughts about possible, AMO-style detector experiments where you can actually look for something like a Casimir effect that you might expect from certain versions of dark energy theories. So there's one that was published this year, in fact. And I think that obviously that would be really exciting if you got to the point that you were able to do something where you could actually measure something directly.
So this is a pretty open-ended question, but so in physics we've gone from like atoms to protons and neutrons, and now we're at quarks. Do you think we're going to keep going? Like it seems like our definition of fundamental particles keep changing, like every few centuries or something.
So this is probably a question for Edward. You want to take that?
It's unlikely that our current concept is the ultimate answer, but it's also anybody's guess how successful we can be at going definitively beyond it. I think for now I'll stick to that answer.
Would any of you like to comment on the interplay of cosmological limits on neutrino mass relative to direct detection?
I think that it's fascinating that, in fact, cosmological limits are in the same range as terrestrial measurements these days, at least within factors of 3 or 4. My discussions with people who are doing such measurements are, first of all, they're very optimistic that they'll be able to improve their accuracy significantly as they go forward. Secondly, they would consider a terrestrial measurement something of value to them in terms of reducing the number of priors that they have in their analysis and perhaps obtaining more accurate information on other parameters that are in this absolutely remarkable, I think it's 6-parameter lambda CDM model for our universe. So I think it's very complementary, the work that's being done in these two areas, and quite remarkable that you're in the same sort of energy regime or mass regime right now in the two cases.
So I guess I will use my powers one last time to terminate the discussion, and I want to thank Berkeley for providing us this platform, our panelists for participation, and of course it was great to have Edward and Saul also in the room, and thank you everyone for coming.